Hello, y'all. Dr. Lee Berry Jr. back as promised with some more physics. I'll do a double pendulum problem and a free fall problem from our first homework from Golds. So we'll go ahead and start with that, utilizing Lagrange's equations. So the first one will be problem number 122. Of course, this one here, obtain the Lagrangian equations of motion for the double pendulum, illustrated in figure 1.4, where the lengths of the pendula are L1 and L2 with corresponding masses M1 and M2. So 1.22. So the double pendulum, I'll scroll to figure 1.44. Figure 1.4. Here we go. So they drew it pretty simply. So we have a line that we'll say is the v-axis. And we have the first pendulum, like so. We have a line for the axis for the second pendulum. And then we have, in this image, the second pendulum is like swinging in a fashion like so. So to duplicate the image a bit and have the image like this. And what we need to do is find the equations of motion for this pendulum. So, yeah, I can go ahead and leave the textbook up. I'll try to give the pendulum image a bit more room on the screen. There we go. That's what we're solving right there. All right. And so we have a mass here. And we actually have one of these in the science building here at SMU, the Fondren building. There's a double pendulum. I spun it a few times. He's just sitting there with a little sort of blurb about what it is and how and the fact that we can get the equations of motion for it, but it's chaotic, meaning that when something is chaotic, a very small change in the initial conditions makes a very drastic change in how it behaves. So if you turn the pendulum to a certain angle and let it go and watch what it does, and then turn it to the exact same angle, just because there will be some error margin with the machinery, there will be some error margin in how far you thought you turned it and so forth. It could be a very, very small difference, but it'll cause it to behave in an extremely different way. So what the problem wants us to do is get the equations of motion for this problem here. So we'll go through that utilizing the available solutions so I can not make any mistakes I made before. And I'll walk through it. So the first thing we can notice is we can put the details that the book gave us, which is theta 1, theta 2, L1, L2, to identify the components of the double pendulum. And the first thing we need to do is identify the degrees of freedom. So I believe it said that this is confined to a plane. Let me confirm that. Let me go back to the question. I had the pendulum drawn now. Double pendulum. It has to be confined to a plane. I don't know if that's because I'm thinking about the one we did yesterday where she gave X, Y, and Z components for this pendulum, which I didn't think to do. I was thinking it was confined to a two-dimensional plane. So this one, it does not seem that that was taken into account. It seems like only X and Y was taken into account. So it must simply be that for a double pendulum, it's confined to a two-dimensional plane, or we could look at the constraint equations as well. So perhaps that's why. Technically, it is three-dimensional, but she's just utilizing the the constraints. So let's say that we have 3 degrees of freedom per particle, 3n. So each one can move in the x, y, and z directions, y, x. But we can actually subtract the constraints that apply to the mechanism. So one constraint we could recognize is that the length, the x component of the first string, so I'll call it x1, like how far this can go over. This is going to be the s component of the first triangle, and the y component. Both of these have some limits. And the same thing with the s component of the second one and the y component of the second one. And what are these constraints? So one thing we know about the top one is that, and confirming with the solutions as well, that the direction it moves on the x-axis is going to relate to the angle. It's going to be limited by the angle. So why don't we do sine of theta 1 equals opposite over hypotenuse. So there's going to be x1 over L1. So x1 equals L1 sine theta 1. And by the same token, y1 equals L1 cosine theta 1. So those are two constraints. So this is going to be 3n degrees of freedom minus 2. And we could also look at the constraints on the third pendulum. to me the second pendulum. So we can say um, x2 is going to be only as far over to the left or to the right as x1 initially. So if x2 is vertical, like there's no x2, it'll be exactly x1 over. And however much it uh, varies will be plus or minus that distance. So we can say it's x1 plus, and what's the distance it varies? It's going to be sine theta 2 is x2 over L2. So x2 is L2 times sine theta 2. And by the same token, y2 equals y1 plus L2 cosine theta 2. Let me check and make sure I have these correct. That seems right. And for kinetic energy for our Lagrangian is going to be kinetic energy minus potential energy. And potential energy, we can take our regular 1/2 mv squared I for each one. So it's going to be 1/2 mi x dot squared plus y dot squared. Y dot plus 1/2 m2 x2 dot squared plus y dot squared for 2. Now notice that she went straight to 2 dimensions. So I suppose it is just I have to ask about that. Maybe I should ask now before I forget. So what I'm going to ask my professor is this. Where did my email go? So what I want to know is, this is question, it was 4, homework 1. Are we using 3 dimensions and then the constraints lessen by 4? Or are we starting with the pendulum, starting with the limit of only the xy plane? And my confusion is why, what was that problem 3? 3, use x, y, and z. Problem 4, only x, y. All right, so I'll send that in. We'll see what answer I get. Welcome who's watching. And if you have any questions or comments, let me know. Drop a line to let me know you're here. I'm checking the comments. All right, so we know with a double pendulum, we just start with x and y. I wrote to ask if what the deal is y. Problem 3, we did both. But we know that n is 2. We have 2 pendula, so 6 minus 4, so we have 2 degrees of freedom. And It stands to reason that for these two, we'll use theta 1 and theta 2 for our generalized coordinates. So the coordinates that'll make this easier to understand. And again, so with the double pendulum, we have our four constraints with the length, well, I guess I should say the displacement and the x and y. So that'll give us a limit on the positions of the bobs. And that's going to leave us with two out of the 6 degrees of freedom for the two particles in 3D. And now our generalized coordinates will be Q1 and Q2. And so what I need to do then, so remember with a double pendulum, we're not doing X, Y, and Z. We're just doing X, Y. So I shall go ahead and convert these. So we need X1 dots. So X1 dot equals, so L is constant. So that's going to be theta 1 dot L1 cosine theta 1. So that's by using the chain rule. We have theta 1 dot, the derivative of the sine will give us cosine. But theta is also a function of t, so you have to get the theta dot with that. And that looks correct. Y1 dot equals theta 2 dot L2 with a minus sine theta 1. And X2 dot is going to be a little bit more complicated. Maybe I should do the squared first. So X1 dot squared equals theta 1 dot squared L1 squared cosine squared theta, and Y2 dot squared equals theta 2 dot squared L2 squared sine squared theta 1. So we have that. And so we'll do X2 dot. So X2 equals L1 sine theta 1 plus L2 sine theta 2. Make sure I got that right. Yep. So theta 2 dot equals, we're still going to have the theta 1 dot L1 cosine theta 1 plus theta 2 dot L2 cosine theta 2. And Y2 equals L1 cosine theta 1 plus L2 cosine theta 2. So Y2 dot equals, that's going to be negative theta 1 dot L1 sine theta 1 minus theta 2 dot L2 sine theta 2. So we have that. So now we have to square it to plug it into the equation. Square them and sum them. So we would have T equals 1/2 M1 theta 1 dot squared L1 squared cosine squared theta 1 plus theta 2 dot squared L2 squared sine squared theta 2. Excuse me, I think I mixed up my ones. Yeah, it should all be 1. And it should all be 2s. See, I did the dot first and then I did the square. So that it. So just made a few typos here. So this would be x1 dot, y1 dot. Go back up. So need to make sure organize this better on the exam. We have x1 dot, y1 dot. So we have dot squared. So this is all 1. Dot of 1. Dot square root of 1. X2. Then I have to square it. All right, so this is looking good so far. So we have x1 dot squared, theta 1 L squared, theta 1, then y1. So let me follow exactly how I have it written up there. So theta 1 squared. So this is this, which is what we have here. Theta dot 1 squared L1 squared cosine squared theta 1. Y1 dot squared is this. So I write that here plus theta 1 dot squared L1 squared sine squared theta 1 plus 1/2 m2. Now I have to square these. So I'm going to have theta 1 dot squared L1 squared. I think I need to write smaller to give myself more room. So I'm going to write this over this whole line. Theta 1 dot squared L1 squared cosine squared theta 1 plus 2 theta 1 dot theta 2 dot L1 L2 cosine theta 1 cosine theta 2 plus theta 2 dot squared L2 squared C theta 2 squared. So we have that plus, now we have to get the x2 and y2 one. Hold up. Let me highlight this. Already got the x2. Need to get the y2 one. So I'm breaking that up into two. 1/2 m2. And I'll make that this one to cover this entire line. So we have theta 2 dot squared L1 squared, theta 1 dot squared L1 squared sine squared theta 1 minus 2 theta 1 dot theta 2 dot L1 L2 sine theta 1 sine theta 2 and pulled up. You look at my negatives more closely. I'll overlook this negative in the front here. So there's a negative in front from the derivative. So actually everything here is positive. Plus theta 2 dot squared L2 sine theta 2 and close that. All right, so we have that. I think that is right. And let me check that my x2 dot is right. So both of those have sine. X1 sine y1 cosine. When you take the derivative, x1 cosine y1 sine with a negative, and x1 squared makes them both positive. So that's why everything in the first line is positive. X1, Y1, pretty straightforward. X2 and Y2 is the sum. So X has the sine, Y has the cosine. So X will be positive still. Y will be double negative for the sine. And Y2 squared, everything is positive. Seems like I should have a negative cross term, but I guess not. All right, let me check the solutions and see. So 1/2 m1 L1 squared, theta 1 squared, cosine squared theta 1. L1 squared, theta 1 squared, sine squared theta 1. And Yeah, two things and initial steps. Oh, I'm just looking at the part where she actually just wrote squared. Squared, squared. So the next line is the writing it out. Theta 1 squared, L1 squared, cosine squared theta 1. Theta 1 squared, L1 squared, sine squared theta 1. We have theta 1 squared, L1 squared, cosine squared theta 1. Theta 2 squared, L2 squared, cosine theta 2 squared, plus 2 theta 1, theta 1, theta 2, L1, L2, cosine, cosine. And then theta 1 squared, L1 squared, sine squared theta 1, theta 2 squared, theta 2 squared, L2 squared, sine squared theta 2. Left off my squared here. And 2 theta 1, theta 2, L1, L2, sine theta 1, sine theta 2. Okay, so that looks right. So let's simplify some of this. So T equals 1/2 M1 theta 1 dot squared L1 squared. Simplify the yellow and blue line plus 1/2 M2 theta 1 dot squared theta 1 dot squared L1 squared plus. So I'm just going to add according to the one above it, which cancels out. Plus, now I'll do this one next. Theta 2 dot squared L2 squared. All right, that works out. Plus 4, no, plus 2 theta 1 dot theta 2 dot L1 L2 cosine theta 1 cosine theta 2 plus sine theta 1 sine theta 2. Close that. That looks right. Two. Right. So let's see what the next simplification is. So this is just going to be long and ugly, I believe. All right. So we have M1 M2 theta 1 squared dot theta 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 2 squared dot half M1 M2. So that's these first terms here plus I extracted out the wrong thing. This is L. This is going to be these two. Is this 1/2 theta 1 dot squared L1 squared, and extract out the M1 plus M2 plus 1/2 M2 theta 2 squared dot L2 squared. That takes care of this one. And then we just distribute the 1/2 M2 theta 1 dot theta 1 dot theta 2 dot L1 L2 C1 C2 plus S1 S2 for the cosines. So let's actually use some trig identities next. This is going to give us sort of a formula, a trig identity sheet if we need those. I mean, they make things shorter and smoother, but I think they're absolutely necessary. I shall leave it like that. And the potential energy. Welcome who's joined. Like, subscribe if you haven't. Let me know if you have any questions or comments. And be sure to drop a line in the chat. Say hi or what have you. So looking at, and right now we're doing a double pendulum problem. So this is the problem here. Let me put the double pendulum back on the screen. I didn't know what page it was on. I believe it was 1.4. Yeah, here it is right here. And this is the problem that we're doing, finding the equations of motion for that. So we have these two pendulum. Each of their potential energy individually will be mghi. So let me put a summation I here. I think I forgot my summation I up here for the notation. So we have mgy1 plus mgy2, which equals m1 g l cosine theta 1 plus m2 g l2 cosine theta 2, if I'm remembering that properly. Let me see. Yep. And interestingly enough, she let this be v equals 0, which I guess makes sense because then it's less to calculate. So if I make v equals 0 down here, then I have to do the 1 minus thing. I wonder, should I try that to see? Let me think. So this is what I'm thinking about. If I make this ground level be V equals 0, right? We can set our potential where we want it to be. So maybe I'll try that and see if I get the same answer. So that means that this height won't be correct. But we'll see if we get the same answer that she got. So what'll happen is, well, we can't even do y1 like that. So let me back up. Well, I have to do h1 and h2. And h will be, here will be, I will say h2 prime. And here will be h1. H2 proper will be all of this. So I can say that H1 is the full L, the full distance, minus what's above L. So I can say H1 equals L minus what is above L, which is L1 cosine theta 1. And H2 is going to be all of that. So it's going to be H1 plus L2, it should be L1, L2 minus L1 cosine theta 2. Excuse me, L2 cosine theta 2. Right? So this should be L1 minus L1 cosine theta 1 plus L2 minus L2 cosine theta 2. So this is going to be L1 1 minus cosine theta 1 plus L2 1 minus cosine theta 2. Much more complicated than the one she did, but I shall try it out just to see what happens. Let me check one thing. I think we're good. So these two heights together will make the heights for each pendulum. Yes, do. The double pendulum is chaotic. So it is a chaotic system, which doesn't mean that we can't understand it. It simply means that a very small perturbation in the initial conditions will cause a very different result. So if you try to start a double pendulum, and they have one of these on the first floor of the building I'm in right now. Right now I'm in a science building at SMU where I go to grad school. So on the first floor there is a double pendulum encased in a little glass case. Maybe I'll actually stream from there one day. I'll take a picture of it. But it is cool to see. But there's a little knob you can turn for it. And let's say you turn the knob and you look at where you turn the knob and you let it go and it spins and does all this crazy stuff. Sometimes it swings like that. Sometimes the second pendulum is twirling around it fast in a circle. Sometimes it flips all the way around. It just does a bunch of crazy stuff. And you watch it and you see the crazy stuff it does. But then you try to turn it back exactly where you let it go the last time. But because there's some imperfections in the knob, so you can't, even if your hand is in the same spot, it's not at that exact spot. And Your eyes may not notice the exact spot and so forth. And when you let it go, you can see it moves quite differently. So yes, it is a chaotic system, but we can get the equations of motion for it. Let's take a look and see what we have here. I'm going to plug this in. So I'm going to have V equals M1G. And this is going to be, by the way, L1, 1 minus cosine theta 1. Mg L1, 1 minus cosine theta 1. Plus, do I have enough room to write this? I don't think I do. Plus M2 V times L1. All right, let me do a bracket here. L1, 1 minus cosine theta 1 plus L2, 1 minus cosine theta 2. All right, so I think that's correct. But again, I'm doing it slightly different from the solutions because I understand this way a little bit better. But we shall see if it pans out in the end. So what things can I simplify here, looking at her simplifications? So I do still see where I can simplify some things. So I can still have, so let me just make a slight adjustment. I'm going to distribute this M2G. So then I will have this like so. So then I can simplify like she simplified there. So I can have M1 plus M2. Mine is positive since mine started from the bottom. So all of these potentials are positive. So it's M1, M2, G, L1, 1 minus cosine theta 1 plus M2, G, L2, 1 minus cosine theta 2. All right, so that's what we have. And so, okay, so see how this works out. So this is our kinetic energy and our potential energy. We know that the Lagrangian is T minus V. So that means the Lagrangian is all of this ugliness added together. So we have this. Just going to copy it down. Minus all of this. And it should be our Lagrangian. So again, it looks slightly different in the solution because my potential is slightly different. But we'll see if we get the same answer. All right. So now we can do our Euler-Lagrange equation. So the Euler-Lagrange equation is going to be full derivative dt of partial a Lagrangian over partial generalized coordinate dot minus partial L over partial the generalized coordinate no dot equals 0. Did I have a constraint equation here? I think I did, didn't I? Let me see if she used the constraint. No, she didn't. She's still using the constraint equations. That's why I used the constraint equations to reduce the degrees of freedom, which I'm still unclear about because we went straight to xy and not xy and z. I sent her an email about that earlier in the video, so she's really good about responding to email. So I'll have to understand that detail. But for now, I'll just have to keep in mind with a double pendulum, you go straight to xy, ignore z, assume that it's in a two-dimensional plane, and then use your constraints to limit the the equations to the two generalized coordinates. So you see how I took uh, the limits of the lengths of the rods and put those in terms of theta 1 and theta 2 and simplify my equation that way. Okay, so let's go ahead and work this out for each one. So we have theta 1. So I'll just take this in pieces. This will be the first thing. This will be the second thing. And this will be the third thing. So I'll do these in pieces. So 1 partial L over partial theta 1 dot is going to be, okay, look at all of this ugliness here. So I see two things with theta 1 dot. Wish there was an easy way to delete this purple line. Let's see if I can delete it without too much fanfare. Yep, that wasn't too bad. All right. So I see two of these things with theta 1 dot, this and this. So I have to take the derivative of those two. So we have M1 plus M2 theta 1 dot L1 squared. Did I put a dot over my L by mistake? Yeah, this is a copy from earlier. We have that plus, so theta 1 dot is just what it is. So I have here M2 theta 2 dot L1 L2 C1 C2 plus S1 S2. Let me know if you think I made a mistake. So then we have d dt of partial Lagrangian partial theta dot 1. So that should be easy enough. M1 plus M2 theta 1 double dot L1 squared plus M2 theta 2 double dot L1 L2 C1 C2 plus S1 S2. And the C1 is cosine theta 1, C2 is cosine theta 2, S1 is sine theta 1, S2 is sine theta 2. I learned that method of abbreviation from, I'm a TA, a teaching assistant for a mechanics lab, undergraduate intro mechanics lab. And the professor, like the way the class goes, the professor usually gives like a 10-20 minute spiel at the start. Then I give like a 5 or 10 minute spiel after that. And then usually the professor leaves and goes and does what he does elsewhere. And I lead the rest of the class and go through the lab. And the professor, he often does this, like when he's writing an equation on the board, instead of writing cosine theta 1, when he gets to the end, he just put c theta 1. I like abbreviated even further and just put C1. So but it's a cool little abbreviation, so I like it. So that should be that. I believe. I don't see any other theta dots. So now we have to do partial L over partial theta 1. So, and I have a lot of these. And that's the benefit of using the big identity, I guess. I have a whole lot of less of those to deal with. But deal with them myself. So let's go ahead and do this. So if I look at this, a lot of stuff is, of course, going to disappear. So again, right now, I'm looking just at that one right there. Oh, and oh my gosh, there's another cosine. There's another theta 1 right there. So those are the two theta 1s I see that I have to take derivatives of. All right. So we have, for the first one, I'll have a negative because it's going to be a cosine theta. When I take the derivative, it's going to go to sine. And we're going to have m2 theta 1 dot theta 2 dot L1 L2 sine theta 1 and cosine theta 2. And the other part of that disappears since there's no theta, regular theta there. Let me think. I'm taking the integral of theta. Do I have to take the time derivative? I don't believe so. But theta is a function of t. Let me take a look and see if she took the time derivative of it. Theta 1. I don't see a theta dot on hers. Okay. So we'll say there's no theta dot. Let's look one more time just to be sure. Don't believe so. I have to work on my details of all these partial derivatives. So I have sine d dx sine x, then we know that is cosine of x. But if x is a function of t, do I then, no, I don't think I take the time derivative. It's just x of t is similar to just x of nothing. Okay, so I'll just go with that. So I think I have that one. And then I have to take the derivative of the other part. So it's going to be, so I have a negative in the front already. And m1 plus m2 GL1. And when I distribute that in to the cosine, that's going to become a positive cosine theta 1. And then when I take the derivative, it'll be a negative sine theta 1. So I believe that is that. So now when I put this together, and I have d dt minus this, the Lagrange equation, I should end up with this plus, since there's already a minus on it, and actually I could just copy it down with the negative and just put the plus on the front. All right, that should be the equation of motion for the theta 1. Let me take a look and see. I did mine slightly differently. But the first part is the same. The second part is the same, except she used the identity here. And the third part, yeah, it's hard to tell. I didn't do it exactly the way she did it. But I believe it's the same thing because I have a whole lot of sines and cosines here, and she has another term with the, what do you call it, the identity for these two. So I believe that that's correct. And all I have to do is do theta 2 the same exact way. It'll obviously come across slightly differently. I can see that the equations are different. Let's go ahead and do it. I was going to see if I can copy that down and change a few things, but I don't think that's going to work. This is 1, 2, 3. So we'll do 1 again. We have partial L over partial theta 2 dot equals. So let's look at this. So the ones I need now are going to be, this has theta 2 dot, and this has theta 2 dot. So we have M2 theta 2 dot L2 squared. We have plus M2 theta 1 L1 L2 C1 C2 plus S1 S2. That seems to be that. Then we have d dt of partial L over partial theta 2 dot. So that equals M2 theta 2 double dot L2 squared plus, oh crap, that zeroes out. Did I miss a zero out part on the first one? Let's see. I did, didn't I? I put a double on the theta 2 instead of zeroing that out. So that means that this whole term will go away. I might be missing a term. Theta 1 dot goes away. Let's see what we get. That is the first one. So maybe not doing the identity really helps out with that. Let's see. Let's keep going. That's the first thing I got. Oh, and this equals 0. So I forgot to set this equal to 0. And then we have on this one, that term goes away. And we have partial L over partial theta 2. So I'm going to have to look at this one. And oh, I see what I missed. I see something else I missed. So the theta 1 only took, so for the theta 1 for the third part right here, I took the cosine here of theta 1, but I didn't take the sine of theta 1. So I'll add that really fast. That's the extra term I'm missing. So that'll be plus M2 theta 1 theta 2, both of those dotted, L1 L2, but then it'll be cosine theta 1 sine theta 2 for the theta 1 that's there. So that means that the full uh, equation would have a minus this at the end. All right. Now let's closer to Professor's answer. All right. Yep. She has a double dot section, a dot section, and something with no dots. So now I have a double dot section here, a dot section here, and something with no dots. All right. And I'll move my equal 0 down. So theta dot 2, I have that there and there. Oh, so I got to do 3. I got to remember that on the exam. And maybe I should copy this down and make it easier to not have to scroll so much. So I have, so now I'm doing theta 2. I think I can do this in a very sophisticated way here. So I can do negative sine 2, and I can do cosine 2. And that should do it for both of those. And what's the other theta 2 dot here? So I can have this. Oh, I already copied it down. Hold up. So this 1 is going to go away. It's going to be a positive cosine. When I take the derivatives, it'll be negative again. And this will be sine theta 2. And that should be that. So let's see how much different it is. Looks like I have these same 3 components again, a double dot section, a dot section, and a no dot section. So it's promising. So I have d dt, this with a minus equals this. That. Right. So those should be the equations of motion equals 0. All right. I think I'll stop there. I could use a break. I've been going for what? Just over an hour. Thanks everybody who joined in. Thanks for dropping a line, Drew. Hope to see you again. And I'll be back later, if not tomorrow, or tomorrow, if not later. I'm sure it'll be tomorrow. And do some more graduate level physics. I'll do the faulting under gravity tomorrow, and maybe something from the homework too. And I'll make sure to finish all the problems by Friday when the exam is. So thank you all for watching. Like, subscribe if you haven't. I'll see you next time.